Okay, folks, it's time to start again for the last block, the last 1.5 hours. You can do it. Isn't it amazing how quickly the day goes by? No, you have a headache? They don't think it's that quick. All right. So 1.5 hours left. We can cover a lot of interesting things in that time. And the topic now is focusing on this combination of continuous and categorical latent variables. We've had some limited examples of that already, like allowing for a residual correlation between items. But now we're going to put it into a more organized framework. And we're going to focus on two things today. Blending continuous and categorical latent variables in the factor analysis setting. And we're going to talk about something that we call factor mixture analysis. We're also going to talk about mixture factor analysis, and I'll tell you the difference between the two. And you can see it as a generalized factor analysis or a generalized latent class analysis, depending on which angle you come from. And we're also going to briefly mention structural equation mixture modeling. The third bullet, growth mixture modeling, we're going to wait with until tomorrow, where we go longitudinal. But I just want you to be aware of the fact that the ideas that we have talk about tomorrow in growth mixture modeling are already begun, are already implemented, the basics of it in the factor mixture analysis model, which is an example of the fact that things get progressively easier as we go forward, not harder. And it's also easier because I keep repeating myself here when I talk about these models now. I'm going to do quite a lot of repetition here. We're going to talk about categorical latent variables on the left and continuous latent variables on the right. And we're going to imagine that in both cases we're working with dichotomous observed variables, dichotomous indicators. And here again now you have the modeling story that we brought up in the context of ADHD, attention deficit hyperactivity. No, attention hyperactivity. Yeah. I'll leave that aside. Anyway, you know the story. Now you look at this diagram and it looks like a very easily interpretable latent class model, right? You wish you got these kinds of item profiles. And you're going to see that we actually see them at times. And you already know everything that there is to know about that model diagram. You have a latent class variable. And you assume that you have correlations between the items explained by, or associations, I should say more generally. The associations among the items is explained by the categorical latent variable. And the categorical latent variable is defined to be such that it is the only reason that these variables are associated, which is the same thing as saying that you have conditional independence. The items are independent given class membership. And once again, I want to hasten to add that that does not mean that the items are uncorrelated. So I don't want you to come to me and ask me, I don't believe in the latent class analysis model because my items are correlated. You know, and we hear that often. The items are strongly correlated because they are influenced by one and the same latent class variable. The independence is within class. Given that you are in, say, class 4, the items are uncorrelated, is what this model says. Now, if you have a lot of direct effects from X to several items, they may not be conditionally independent just because they're influenced not only by C but by X. So if you condition on C, they're still correlated due to X. So having X with direct effects takes care of some of the violation of conditional independence. I should also mention something that came up in the break here. Somebody asked me, sometimes I get a lot of fixed thresholds, fixed at high or low values. Is that bad? And that's not bad, because look at class 3 here. Here the thresholds are very low, and therefore giving a probability of 1, so that if the thresholds are low enough, you would have exactly probability 1 of endorsing all of the inattention items if you are in class 3. That just makes the interpretation more easy. So thresholds fixed at high and low values, which Mplus does automatically when they get large, is not bad. It actually helps the interpretation. And that happens particularly when you have polynomous ordinal indicators, such that for some classes not all of the indicator categories are realized in the data for certain classes. Anyway, so this model is now standard LCA with an X and potentially direct effects. But let's ignore the direct effect aspect. So then let's go to the right screen. And again, the items are dichotomous. And the picture on the left then is y-axis, the item probability. And now we're going to have a continuous latent variable on the x-axis. So there's a factor f, a continuous latent variable, which influences the response to the items. So now you go back to the first slides that we went through and think of logistic regression here. This is logistic regression. That is, the probability that the item gets endorsed is a function of the factor. As the factor increases, the probability of endorsing, say, item 4 increases. And here we see that the items differ in not only in their thresholds or intercepts, but also in their slopes. So as the factor increases, item 4's probability of endorsing item 4 increases slower than items 1, 2, and 3. So there are two parameters, intercept and slope, where, again, intercept can be translated into negative threshold. So this is the situation of item response theory, IRT, also called latent trait theory. All it is logistic regression of the item on the factor. It's just that the factor is a covariate, right? The only thing being that it is latent, not observed. So we draw the picture as on the right, factor with the 4 items. So this is now, this arrow represents one logistic regression of item 1 onto factor f, a continuous covariate, albeit latent. So it has an intercept and a slope and can be drawn like this S-shaped curve, like in the coal miners, smokers, non-smokers situation. Each of the item has its own intercept, or threshold that is, and its own slope. Typically, in IRT, you have only one latent variable, one factor. Typically, in IRT, you don't have an X variable. So in topic 2 that you have on our website, a video, we talk about IRT a little bit more and describe how this kind of modeling relates to standard item response theory, which is used in educational measurement and testing. Typically, you have no X variable, and typically you assume that the F variable is a normally distributed factor. Typically in IRT, F is an ability to solve a certain item, an educational item, say a multiple choice item. Now, these two models can be tested on data. So if you have a set of diagnostic criteria for, say, substance use of some kind, substance use problems, you will have a set of diagnostic criteria dichotomously scored. And the question is the model on the left more suitable or the model on the right? And the model on the left has the advantage that you get a classification of individuals into different classes. But The model on the right allows for a continuum to be represented, perhaps a more fine-grained picture. On the other hand, you don't get any classification of individuals. It's true that you can say that individuals who are higher than a certain threshold here, a certain high value on the factor, people out here have a problem and those who are below don't. But the data will not tell you much about the cut point. Even if you estimate the factor scores, you will not easily see a natural cut point, whereas this model works, produces cut points, produces a classification of individuals. So over here, then, you allow for the correlation between the items through a factor, and the correlations among the items is higher when the factor loadings are higher and when the factor variance is higher. If you know your factor analysis, you know the correlations increase by the factor loading size and the factor variance. So that's just a repetition of what we've done. Linda applied these two models for the alcohol diagnostic criteria and found that the factor analysis model, although with two factors, fit the data better than the latent class model. So now let's get to a new model. Putting all of these on the same slide. I'm going to stand the other way, actually. You have the three models again here. You have your big modeling picture here. Say that you work with two classes for simplicity, starting at top left. Individuals who have a problem and who don't have the problem. And you draw the latent class model like this. And to repeat what we said, the description can be given in the following way. If you take a pair of items, J and K, they are strongly correlated because they're influenced by the same latent class variable. As long as you have at least two classes, they are correlated. If you only have one class, they're uncorrelated. You only have one class in the latent class model that says that the items are uncorrelated. That's a pretty uninteresting model. But for, say, in this case, two classes, you say that within class, the relationship between the items is nil. There is no association. That's the definition. If you go to the factor analysis case, or the IRT, or the latent trait case, you have a continuous latent variable making them correlated. There's not an interesting picture to draw. We can ignore this picture here. What about, as somebody already suggested, what about combining the models? Well, let's consider that. I don't know if this blocks. You can look down to the left here. The podium might block some of you. You have, I'll point over here. You have both a latent class variable influencing the items and a factor, continuous variable, influencing the items. So one way to understand that is to look over on the left here. So you still have two different profiles, high and low, and that is handled by the latent class variable. The latent class variable influences the items, shifts the probability up or down, depending on the class, up or down. That's what these arrows do, given the latent class flavor to the model. But then we speculate that there is variation among the individuals even within class. So in class 1, there may be individuals who have a rather low, comparatively low tendency to endorse the item, and some individuals in class 1 have a relatively high tendency to endorse the item. So you have this severity variation, which has been of interest to diagnostic researchers. They feel that sometimes these classes are too broad. There is too much heterogeneity among individuals within a class. And here's a statistical attempt to pick that up, that idea of further severity variation within class, within each of the classes. So that is then handled by adding a factor variable, a factor that influences the items like this. It says that the probability of item 1, say, is influenced not only by being class 1 versus class 2, but for increasing severity, the item probability increases in line with the IRT model up there in the middle. So with increasing severity here, probability increases. That's one way of looking at it. The other way of looking at it is that factor mixture analysis generalizes the latent class approach in the sense that you no longer have to have a model that specifies conditional independence, flat regression lines, but you can allow for conditional dependence. So positive within class lines. That is, you allow for within class correlation among the items. So, even when you are in a certain class, there is another variable which makes the items correlate even within the class. So there could be reasons why item responses are more similar for individuals within the class, and the reason is the severity variation within the class. So this is more general. You can allow for positive correlation. It's a model that has been used in genetic context in microarray analysis by McLachlan, the same McLachlan as in the McLachlan and Peel book. And he argued on substantive genetic grounds that it would be more realistic to allow for this degree of estimated within-class correlation when you seek to find these latent classes or clusters of individuals. He actually did an exploratory factor analysis model within each class. So an exploratory factor analysis mixture model, which we now have, since a couple of versions, have incorporated in Mplus. So you can actually do exploratory factor mixture analysis. It's in one of the chapters in the user's guide. And we have also worked hard on making it practical to do maximum likelihood analysis of factor mixture models where the items are not continuous, as in McLachlan's case, but categorical or otherwise non-normal. And apply that to different kinds of data. I should say that my experience to date is that this model typically beats the models above it. This model typically has a better BIC than either the factor analysis IRT model or the latent class model. It's a little bit more complex to interpret, but it often comes closer to the data, and it's a model that I think you should consider. And like I said, it's also a model that ties directly into the models of growth mixture modeling that we'll talk about tomorrow, where F corresponds to the growth factors. And there are many variations on this theme, and I will actually show you another summary page after Linda has presented two examples on the factor mixture idea. So I'll turn it over to her now.
Okay. Let me do this first. Okay, so we're going to, on the right screen here, this should look familiar. This is just a repetition of what we've already looked at. But just so we're going to be looking at the data, the alcohol dependence criteria again. And we looked at the LCA model with 3 classes and the factor analysis model with 2 factors. And now we're going to look at the FMA model and see how that fits the data. So if you remember, we use BIC for relative fit, relative model fit. And with our LCA 3-class model, we have a BIC of 28,539 with 29 parameters. And we improved the BIC with the factor analysis model with 2 factors. And if you look at the F factor mixture analysis, 2 classes, 1 factor, with the factor loadings invariant, the BIC with 29 parameters goes down to 28,370. So implying that this factor mixture analysis model is a better fitting model for these particular data. Now we can also compare with respect to absolute fit of the data, looking at standardized bivariate residuals and standardized residuals for most frequent response patterns. And as we've said earlier, you obtain these by asking for Tech 10 in the output command. So here we have standardized residuals for various observed frequencies. So here we're looking at our standardized residuals for the latent class 3-class model, the factor analysis 2-factor model, and the FMA 1-factor 2 class. And these are for the response patterns, I believe. So, for example, I told you in Tech 10 we can look at univariate and bivariate residuals, and then also residuals for the response pattern. So, for example, we have 9 items here. A response pattern would be 9 zeros if a person endorsed none of the items, 9 ones if they endorsed all of the items. If they endorsed the first 3, it would be 1, 1, 1, and the rest zeros. So there's a certain combination of response patterns available, and we look at residuals for each response pattern. And what you see here is that and the residuals are standardized, so we're looking for values, absolute values greater than 1.96. The observed frequencies are shown in the first column, estimated frequencies in the second column, the fourth and the sixth, and the residual in following those. And you'll see that we have 3 residuals for 3 response patterns that have like 600, 200, and 150 observations each for the latent class model. For the factor analysis model, we also have 3 large residuals. They are for a smaller response pattern, for response patterns with smaller frequencies. For the factor mixture analysis with 1 factor and 2 classes, none of the residuals are larger than 1.96, have an absolute value larger than 1.96, which would imply that these fit the data better. The factor mixture analysis 1 factor 2 class model fits the data better than the other 2 models that we looked at. So let's take a look at how we would set this model up in Mplus and see what's new here in the input. So I think there's nothing new until we get to algorithm equals integration. And when you have maximum likelihood estimation, which we have here, and categorical outcomes with a continuous latent variable, or a factor like we have in the factor mixture analysis, we need to use numerical integration to estimate the model. So that's why we have this. And each factor is 1 dimension of integration. So in our situation, we'll have a single dimension of integration because we have a single factor. You can see the starts have been increased, and then the ST iter has a default of 10. So this is the iterations for the initial stage analyses. So for these 200 random starts, usually we just do 10 iterations for each of the 200. And here we've increased it to 20. And it's the second number, the 10, that we carry to complete analysis. And we've turned adaptive quadrature off. The default is that it's on, and that sometimes it just works better with it off. You can see that we have the option processors. Processors equals 4. So if you have a computer with multiple processors, then you definitely should use that option. It will speed up your analysis considerably. So there's one other thing that we don't show here that will also speed things up. So if you have multiple processors, if you put after the number of processors parentheses starts, end of parentheses, then that in addition spreads the random starts across the multiple processors in a way that also makes things even faster. So you might, for those of you who are running analyses that take a long time, you might want to make a note of that, the starts setting of the processor's option. Oh. Okay, so let's take a look now at the model command and see what we have. So what we've done here is to our latent class model, we've added a continuous factor, and we refer to that as F. And the by option, so this is the first time you have seen the by option, is short for measured by. So we needed a way in Mplus to name the latent variables. So we name the continuous latent variable F by saying F measured by x1 through x9. And we give a starting value in the second line, F starting value of 1. You don't have to do that, but that's just to show you what that is. And you'll notice in square brackets, we refer to means, intercepts, and thresholds. In this situation, we're referring to the mean of the factor F, and we're fixing it at 0. And the reason we're doing that is because in the classes, so in the class-specific part of the model command, we are freeing the thresholds so that they're different across classes. That when you have a continuous factor in the model, the default in Mplus, whether it's multiple group analysis or multiple classes, we hold the thresholds equal and the factor loadings equal across the classes or groups to represent measurement invariance. So when we relax the assumption of the thresholds being equal by mentioning them in the class-specific part of the model command, then we have to fix the factor means to 0 in all classes for the model to be identified. So that's why that's done. And this model has the thresholds unequal across classes, factor loadings equal. If you were starting this analysis, you might want to just start out with the default model, which would be F by U1 through U9. And in that case, not have any of the other statements here as a first step. But we're sort of showing you the final step. And then to go through the output. And there's quite a lot of output. Do you want me to go through pretty much? Okay. Briefly, okay. So for each class, we obtain our results for the factor analysis, F by, and we have the factor indicators here. The estimates are logits because in the regression of the factor indicators, which are binary on the factor, which is the factor model, and with maximum likelihood estimation, we get logistic regression coefficients here. And you can take a look at this to see which of the items are most important. For example, U9, U5, carry more weight in this severity factor than some of the other items like U2. And I don't remember exactly which they are, but you can look back at the thing to see that. So we give you these results, and then we give you the mean of the factor, which, remember, we fixed to 0 in both classes because the thresholds, which we show here, are not held equal across classes. And then we give one more thing that's important here, and that's the factor variance. So we estimate the factor variance in each class. And you can see there is significant variability. And then we have the I'm just going to go through this. I guess I'll do it on this screen. The same thing for class 2. So for class 2, we have the factor loadings, which are the same as in class 1 because we held them equal. We have the mean 0 because we fixed it at 0 because the thresholds are allowed to vary. And then the factor variance, which is larger in class 2. Categorical latent variable means just simply tell us how many convert into the probabilities of how many people are in each class. So we get the means for the one category of the variable, and this would be translated into the probability where we see latent class membership. So that's just simply related to how many people are in each class. So then this is a plot of the classes for the 2-class, 1-factor model. So you see, if you remember back to the classes we saw in the 3-class model, we had a high class up here where, people were kind of going like this. And we had this class that had the 2 items that were particularly high, and then we had our lower class where larger was the only item that had a probability that was very high. Here it was larger and major roll hazard like drunk driving. So by adding the factor, we've gotten rid of the high class, and instead we've ended up with a problem class, which is class 1, and a non-problem class, basically, which is the class 2. And the factor then varies within class. So within the problem class, people, I would imagine, have higher severity scores. They start higher and go higher than in the normative class, which probably has lower scores. But so taking into account the factor, the severity factor, reduces the need for that 3rd class, and and seems to fit the data better than trying to depict that as a 3rd severe class. So that's my very untheoretical interpretation. So we're going to now look at another example of this type of analysis, and this is an analysis that Bengt alluded to before, but this is a UCLA clinical sample Bengt has worked with of 425 males ages 5 to 18, and they all have been diagnosed ADHD. And they were assessed by clinicians, by direct interviews, and by interviews with the mother about the child. And then they were given 9 inattentiveness items and 9 hyperactivity items that were scored dichotomously. And the children included needed to have the family had to have at least one ADHD affected child. So we wondered what type of classes of ADHD would come out of this analysis using the inattentiveness and the hyperactivity items. And on your right screen are the items themselves. So, they're pretty clear. The inattentiveness items is difficulty sustaining attention and easily distracted, hyperactivity, fidgeting, difficulty remaining seated, blurts out answers, etc. So this is just there for your own information. Now we looked at several different models. The LCA 2-class, 3-class, 4-class, 5-class, 6-class, 7-class. Now if we look at BIC, the lowest BIC indicates 3 classes, but if we look at the BLRT results, which are in the last column, then that would indicate 6 classes. So we took a look at the plots, And so if we take a look at the three-class solution, we see we have one class up here that seems to be high on all the items. And then we have a class that's high on the inattentiveness items, but is low on the hyperactivity. And then another one that is higher on the hyperactivity and somewhat lower on the inattentiveness. When we look at the sixth factor solution that the BLRT suggested, it really is hard to see anything very clear about the classes. So based on that, we decided to look at to settle on the three-class solution. And then what we did is we did an EFA. So what you see here is what you already saw, but at the bottom is what's new. It's a two-factor EFA, which has a considerably lower BIC than the three-class LCA. So it seems to fit the data better, but does not really give us information on classifying children as hyperactive or ADHD. So then we went on, and so what's new on this slide is at the very bottom. So then we decided to do an FMA two-class, two-factor, and that one was with measurement invariance being thresholds and factor loadings held equal, and then also an FMA two-class, two factors with class-varying factor loadings, so where the factor loadings are not held equal across classes.
It's a little complex there. You have a lower BIC for this model, where the factor loadings are invariant, but you should not always listen to BIC, because we'll tell you that now at the end of the day, right? When you have these two models are actually nested properly, and this model has class varying factor loadings, here they're the same, you can actually test those two models against each other by a likelihood ratio test.
So in the corner here is the result of that test, and that test found that this model, using that, having the measurement invariance makes the model fit worse. So we decided to look at this model where we don't have measurement invariance.
And it still has a better BIC than the other models.
Exactly, and it still has a better BIC than the EFA and a better BIC than the three-class. Okay, so let's take a look at these the three new models that we've considered over here, and see how they look, how they compare to each other. And that's another good thing to do. If you're doing all these things and you can't see the progression and how it makes sense that it goes along, then probably something's wrong. So here was our original three-class model, here's a three-class model where we have high everywhere and high on the inattentiveness, low hyperactivity, and high hyperactivity, relatively lower inattentiveness. And then the sixth class we decided didn't really make sense. But here, and the question I guess that people have is there really a hyperactivity class? Or is it really only inattentiveness and hyperactivity is just something else that these children exhibit? Or is there a hyperactivity class that is different and that's predicted by different covariates than the inattentiveness class? So here what we would see is that we have a class high on everything and a class high on inattentiveness, low on hyperactivity, but we don't find the hyperactivity class. The green one here doesn't show up. And it seems that the factor in this factor mixture analysis with or I think there were two factors actually, that those factors seem to take into account the hyperactivity dimension and remove that from this. And although we have the hyperactivity is low here in the inattentiveness here, so it's more an inattentiveness class and a just general ADHD class. I think you should say more about that since it was your study.
So just to say a few more words about these two examples. Indeed, as Linda said, there are two factors here, and they come out very clearly as an inattentiveness factor, severity dimension, and a hyperactivity. It's very clear two-factor solution. And in fact, you can specify it as a CFA, confirmatory factor analysis model. You don't really need the exploratory EFA cross-loadings. It's a very simple structure for those of you who are familiar with factor analysis that is used. And it seems like by introducing those factors, the severity that allows for within-class correlation between the items, simplifies the picture from the 3-class to a 2-class phenomenon, which then is of substantive interest because psychiatrists are really debating whether or not the hyperactivity only class really exists. And it doesn't seem to exist when you use this treatment sample, at least. It's not a general population sample, but a treatment sample. When you go to this model, the FMA model, factor mixture model, that seems to fit the data better. Now, in this first example that Linda went through, you ended up with 2 classes and 1 factor, 1 severity dimension, and here the severity dimension had loadings that were invariant, whereas over on the left they didn't. So over on the left, the severity dimensions were slightly differently defined in the 2 classes. But here, you don't get the the class with alcohol problems of all kinds, that is the overall high combined class, doesn't show up here. But instead you have the peaks here of drinking larger than you intended, and a major role which is dominated by items having to do with drunken driving. So this high class really does look like an abuse class. And in fact, although you have severity dimensions, which makes the probability of an item like tolerance possibly going up quite high. And if you do these plots of FMA results, you really should have severity bars plotted here, say plus minus 1 standard deviation in terms of the factor variation. But I think this illustrates the fact that in general population surveys, it is very hard to capture an alcohol dependence. Wow, thunderstorm coming here. It's very hard to capture a dependence class. You know, alcohol dependence or any dependence is supposed to be dominated by high probabilities of withdrawal and tolerance. Those are the 2 hallmarks of dependence. And I think it's very difficult in a general population survey to actually measure those. People misunderstand them. Withdrawal is confused with nausea from hangover effects, for instance, which is not necessarily an indication of alcohol dependence. So maybe in this sample at least, and this survey, this result, which points to an abuse class of varying severity and a normative class, no alcohol dependence class, may be a reflection of the difficulty of measuring alcohol dependence. At least that's how one can reason about these results. Now I want to show you a few more slides taking this further into more generality. Excuse me. And in doing so, I will get into an issue that we will only briefly talk about today, talk a little bit more about tomorrow, and that is categorical. On the left screen here, slide 177, categorical outcomes plus continuous normal latent variables have the computational and statistical disadvantage of heavy computation due to numerical integration. So Linda alluded to something called numerical integration, which we don't know what it is, but it is something that's an algorithm to produce maximum likelihood estimates. And the need for that comes a combination of maximum likelihood, continuous latent variables, and categorical or other non-normal variables. Those three things together gives you a need for numerical integration. And if you don't remember to say algorithm equals integration in the Mplus input, Mplus will tell you that you need to say that. That leads to heavy computations. The more factors you have, the heavier the numerical integration. We're going to talk about that a little bit at the end of tomorrow, I believe. And that's the computational disadvantage, and the statistical disadvantage is that of having to assume normality for the continuous latent variables. And having to assume any distribution for latent variables is much more serious than having to assume distribution for observed variables. For instance, for observed variables, we know that normality assumptions can be made, and estimation can still give good results. Point estimates are good, and you can correct for deviations from normality by computing non-normality robust standard errors and test the model fit. We'll talk about that in topic 1. But when it comes to latent variables, you're more dependent on the assumption. So there is a way out of that that's called non-parametric approaches, non-parametric latent variable distribution. Using a non-parametric latent variable distribution avoids the normality assumption and at the same time the computational disadvantage. So we put an exclamation mark on that, so in line with chess, that's a good move. So that leads us to this wallpaper of models, which is from that hybrid paper that I mentioned to you. And here we have a thunderstorm in Berlin. It chased us from Sweden, where we were surrounded by water for 1 week. And we're almost hit by lightning. So this comes from that hybrid paper, the 2008 chapter in the mixture book. We'll have the reference a few slides forward. And you can talk about, at this point we've seen so many models, you need a little classification scheme, whether you want it or not. And here's an attempt to sort of structure the modeling opportunities. First, you go from the top, you ask, should your model have measurement invariance? And we go down the yes path first, because we typically want measurement invariance. And then you have a factor analysis emphasis. And then you ask, do you want a parametric factor distribution, by which I mean, should you assume normality? Yes. Or should you not assume normality? Normality gives you mixture factor analysis. Note that that is not factor mixture analysis. And you will see the difference in the 4 diagrams that are coming here. So the leftmost arm here, mixture factor analysis. You have a factor analysis model, and then you have C pointing to the factor. What does that picture now, at the end of the day, tell you? C pointing to F says that the mean of the factor varies across the classes, right? So that corresponds to the picture bottom left. This is one class with a low mean, another class with a high mean. Within each class, you have a residual arrow saying that there's variation in the factor within class. So you have a little variation, less variation for the low class, more variation for the high class. Note then that that's all you need to say for following this path. Now, let's go down measurement invariance, yes, but not a normal factor distribution, and talk about this non-parametric factor analysis. That looks like this. Very similar to what's on the left, but we have left out a little residual here. And therefore, you can characterize the factor distribution by histogram bars, in this case 4 bars corresponding to 4 classes. So this picture is saying that the mean of the factor changes by class, so low, higher, higher, higher mean. So these are the means of the factor. But within each class, there's no variation. Everybody sits in the same bar. There's no bell-shaped curve around it. So here you have a way through mixtures to characterize the factor distribution. The spacing on the factor axis is done by the factor means varying across classes. The height of the bars is characterized by the class probabilities. So a lot of people in this bottom class and fewer people in the high class. This is a non-parametric approach. So if you don't want to work with normal distributions for latent variables, you can take this non-parametric approach. And in the user's guide, you have examples of how to do that. Now, if we go down the measurement invariance no path, then you're leaving the factor analysis emphasized a little bit, and you're more into cluster analysis. More into cluster analysis. When I say cluster analysis, I also then include, I specifically think of latent class analysis. So let's go down the parametric factor distribution. That is, parametric means, say, assuming normality for the factor, yes. Then we have what we just talked about, factor mixture analysis. So look at the picture here now. It's the picture we talked about. C pointing to the items, changing their probabilities or their means across classes, but allowing for within-class variation in the severity, and therefore allowing for within-class correlation, like we show here. What's the difference between this picture and the pictures on the left? Just to help you think about these. That's right. Over here, we have C pointing directly to the items. And actually, in this case, C does not point to F. So in this case, we said, Linda said this, well, she said the item probabilities change across classes, and therefore we cannot also identify and estimate factor mean differences across classes. So we cannot have arrows from C to the observed variables and an arrow from C to F. That arrow would not be identified. But in the picture, I'll take a pause there for a second. But in the picture on the left, you have no arrow from C to Y, which says that these two pictures have no arrows from C to Y, which says that you have measurement invariance, right, across the classes. No direct effect says measurement invariance across classes. That means that the item probabilities in the categorical case are the same. Those parameters are the same. Conditional item probabilities are the same across the classes. And the change in the item probabilities is orchestrated by changing factor means, which is this path illustrating. So the factor means changing is what changes the ultimate probabilities, not the item probability parameters. You see that? So this can be used, this is sort of mixture factor analysis, either parametric, allowing for people who are different means on the factor, and measurement invariance, and then you have the non-parametric version of it still with measurement invariance. But this model is not of that kind. It is concentrating on sorting people into classes, allowing for measurement non-invariance. And in fact, this model often fits much better than these models on the left. Very often, these models are rejected because you don't have measurement invariance across the different classes. Although there are some exceptions of that, and one exception being the growth mixture model that we're going to talk about tomorrow, where you do assume that you have invariance here, same growth shapes in that setting for different classes, but the growth factor means are different and change the means of the observed repeated measures. Now we have one more path to go down, no measurement invariance, and not the parametric factor distribution, no normality. So we have the non-parametric FMA, which I haven't seen used very much. People are catching up with these things, but it has a possibility of, in some models, actually estimate F on C, and in some cases it can be identified. For instance, you could have a model where you have non-invariant loadings but invariant intercepts, and you can estimate this factor model and allow for a non-parametric FMA. So there are possibilities here. I don't want to talk about it now because it's too technical, but there are possibilities for non-parametric FMA as well that haven't been utilized. And if you want to read about this, you have a series of papers. Here is the microarray. There's a microarray book, and in addition to McLachlan-Peel book, there's a specific microarray book that deals with factor mixture analysis. Gita Lupke and I have done some work on that, and I did 2 papers referring to substance abuse, one in addiction for the Alcohol Institute in Washington, NIAAA, and the other for the Drug Institute, NIDA, in Washington. So this article I did first, maybe this one is a little bit clearer, talking about alcohol up here, talking about tobacco down here. And here's the overview paper that had that previous picture in it. And all of these are on our website. Here's the behavior genetics application. Now, here's just a slide to say then, last few minutes, that you can do EFA, exploratory factor analysis, mixture analysis. You know, when you go through these models of latent class analysis, factor analysis, and factor mixture analysis, when you come to the factor mixture stage, you usually don't need as many factors or as many classes as have been chosen for the latent class and factor analysis models. So, you know, if you can sort of compensate, you need fewer classes if you have a factor in the model, and vice versa. So it could be useful to do an exploratory analysis like this one here, where you say you start with 2 classes and you ask, how many factors do I need? Well, you have this EFA, exploratory factor analysis approach that we talk about in topic 1, where you first do a 1-factor model and then a 2-factor model. And the 2-factor model is exploratory. You don't specify whether you 0 and non-zero loadings are going to be, but you have an exploratory approach with rotation of the factor loadings to see what makes sense. And that model is then using class-varying intercepts and thresholds, which is the model that in Linda's previous 2 examples, and class-varying loading matrices, so each class gets its loading matrix rotated separately, and class-varying residual variances and class-varying factor correlation matrices. So everything is free and exploratory. And this is the example of User's Guide 4.4. So that's how you set it up. So that could be useful in trying to figure out the combination of classes and factors. So you really have to go and explore all combinations of number of classes and number of factors. Now, just a few introductory words then about more. So we go from factor analysis to structural equation modeling. Here you have a model. Now we can get more sparse in terms of presenting the models. So what does that modeling scheme tell you? So we have a rectangle here, which means we have a set of items. Could be a measurement instrument that says Y, so apparently the variables are continuous. We have F, so we have at least one continuous latent variable or factor. And we have C pointing to F, and C does not point to Y. So that says that we have a mixture factor analysis, right? Not a factor mixture analysis. And then we have a new feature here. And that is a path model upstreams from C. So C is influenced not just by a covariate being a variable that's not predicted by any other variable, but it's actually C is predicted by a y being the notation for a dependent variable. So we say that substantive theory tells us that X influences Y and Y influences C. Therefore, X influences C indirectly, so Y is a mediator in the influence of X on latent class membership, which then influences latent variable model out here. This is just to show that an example that you can have models in this part of the model, the part of the model that predicts C. You can have a model behind explaining the class membership. And we will see that in the longitudinal setting tomorrow. It will become more tangible and more understandable in terms of longitudinal examples. But it is possible technically to do this in the maximum likelihood framework in Mplus. Actually, the idea for this came from a discussion with an alcohol researcher in Missouri, Ken Shear, who was asking, could we do something about modeling variables upstream from C? So we thought for a couple of years about that and how to do that and how to implement it. You know, the algorithms behind doing the maximum likelihood estimation are quite complex, and we're really thankful that we have Tia Marasporoho helping us do that right. So we presented this to Ken Shear and said we had solved the problem and showed him this, and whereupon he said, oh, that's not what I meant. So, well, somebody else could benefit from it. Here's another one. What does this model tell you? Well, you have a factor analysis model for use. So this looks like an IRT model, like the response area model, latent trait model, one single factor influencing a set of binary items. And that factor influences latent class membership. So again, it's not an X influencing C, but it is rather a latent variable created by, informed by binary indicators. And then you have a latent class model out here. So it is a structural equation model in the sense that you have measurement models and you have the structural part, F influencing C. And you have a setup for that here, which you may want to study, but I don't think we should do that this late in the day. It will just be painful. Instead, we'll go to slide 194 and allow for a little bit more time for a discussion. That last model has been actually, it's not just hypothetical, it has been used in this article in Biostatistics, a good statistical journal. Now, when it comes to structural equation mixture modeling, an early article is that by Jedidi, Jagpal, and DeSarbo in Marketing Science, as an example of the variety of journals that these good statistical ideas appear in. This has to do with structural equation mixture modeling. You can do this modeling in Mplus. You can do that modeling in Mplus. And here is a good psychometric article by a former student at UCLA. I was in his dissertation committee, and I remember how hard he worked on this mixture modeling, confirmatory factor analysis. He looked at many of these factor mixture models and mixture factor analysis models. But it was in the early days, and he said at the end of the dissertation he would never do mixture modeling again. But now, 10 years later or so, he's actually starting again. It takes about 10 years to recover from an analysis of this. All right, so with that, folks, we've come to the references here, and it says that to request a Mutian paper, you should email me at my UCLA email address. But you know, those papers are now either on the Mplus website under papers, or they are on my UCLA website, which you get to from the Mplus website. So you are likely to find all of the papers on those two websites. But feel free to email me anyway if you want to. And then you have all of these general references that we talked about. Sorted by here, you have IRT references, for instance, over on the left. Item response theory references, and seems to be a little bit biased towards Matian references. And well, there's a lot to study in this area. So with that, let's turn to you and ask if you have some final questions. And we have the microphone here.
Whoa, don't fall.
Thanks for the presentation. What I'd like to ask, you've shown a lot of models where you had two classes, maybe two factors. Say you have a situation where you want to model a large number of potential classes, like a large number of symptoms which might predict a diagnosis. Is that possible, or does it create its own difficulties? Say you had, 50 symptoms or more.
So is the question, do we have any specific problems when there are many variables in the analysis? Do you want to take a first stab at that? No?
Not really, but I haven't seen that be problematic. But if you have a lot of items and you've worked with them long enough to know which of them are more reliable and more valid measures of what it is you're measuring, then I would say use the better items. So a smaller set of good items is going to probably get you further than a larger set of not so good items. But
I think we can handle quite a large number of variables computationally without you having to wait too long. These models rely on conditional independence quite a lot. The numerical integration does not really get hurt by the number of items. It's more number of people in some of these analyses. So I would say certainly 100 variables could be easily done.
right.
And I think, I don't see that as particularly problematic.
So it's also, with numerical integration, it's the number of factors, not the number of items. So if you tried to have 6 factors, for example, that could be problematic. I mean, we recommend no more than 4 dimensions of integration, and each factor is 1 dimension of integration. And another comment on this, because I don't know if you're coming from a place of experience where you've had a slow analysis, probably maybe not. But a lot of times, if your analysis is very, very slow, you are very likely trying to extract maybe too many classes from the data, and it may more be a sign of a misfit between your model and data. And if you send that to us at support@statmodel.com, we can give you we can look at that in a way that you can't and tell you if that's what the problem is.
That's an interesting comment, because it is true. A very good statistical fit index is computational time and difficulty in replicating the best solution. They are great indicators that you're trying to either fit the bad model, or more likely trying to pull too much information out of your data that is not easy to find.
And it's fairly easy for us to determine if that's the case. So I always hate it when somebody goes, I've been working on this for 3 weeks. And, I feel like, well, why didn't you email me 3 weeks minus 1 day ago?
Yeah, that's right.
Because it's no fun just to beat your head against the wall.
And Linda tends to answer emails pretty quickly.
Yeah, I do.
At least before 3 weeks.
Right.
I think you have a 24-hour turnaround?
Well, I try. So if you send me an email and you don't hear back from me in 24 hours, it's probably gone to cyberspace. So you should probably send me another email.
I have 2 questions. I'm not sure if the first one is a stupid one. You have sometimes p-values are of 999. I don't understand it. For example, on page 163.
129?
Okay, so the question has to do with p-values of 999.
Oh,
That's for really good models.
No.
What's that?
Whenever
No,
you, well, anytime you get 999, that means that something was not able to be computed. So I can't.
Or it wasn't relevant. So you
Or
get
it wasn't relevant. For example, it was a fixed parameter,
Right.
and a p-value wouldn't be relevant. I'd have to see the output to say for sure, but which slide is it?
163, for example.
163?
Fix okay.
Yeah,
Okay,
so-
so that's a fixed parameter. In the factor analysis model, f by, we fix the first factor loading to 1 to set the metric of the factor. So 1 is a fixed value, so it has no standard error. The ratio is not computable, and therefore there's no p-value.
So 999 is our way of saying this is either not computable or not relevant. In this case, it's not relevant.
Okay.
That's our
the
time.
second question. Is it in LCA necessary that there is a balance between the number of items for each dimension, for example, for inattention and hyperactivity?
So I think your question is, does the number of factors relate to the number of items?
Number of items for each dimension. If it must be a balance between them.
Oh, must there be a balance between the number of items per dimension?
Yes.
Not a very exact balance. If you know nothing about, I mean, we talk about this in topic 1, you talk about EFA, and you want to design a measurement instrument where you have enough items to capture each of the factors. And if you go in and do a totally exploratory analysis, a factor represented by, say, only 2 items may be hard to detect in the presence of everything else, every other factor that is relevant. But the fact that we had 9 items per factor here is not important. It could be 3 items on one factor and 12 on the other, or 15 on the other. So that's not critical. Is the solution dominated by one dimension? No, I wouldn't say so.
Not in confirmatory factor analysis, I think. I think it would be dominated in exploratory factor analysis.
Well, if it depends on if you go down to 2 items, I think it would be. But 3 items, even in exploratory analysis, the factor with more items would not dominate. No. I think that's more of an issue in perhaps principal component analysis. So I don't see that as critical here. Okay.
It's a question for slide 175.
175?
Yeah. I still don't understand why you turned to choose an FMA with 2 classes and 2 factors rather than 3 classes and 2 factors or 3 classes and 1 factor.
So is it this?
No.
Yeah, so the question is, why do we do 2 classes, 2 factor, and not 2 classes, 3 factor, or...
No, why not 3 classes? Because that's what your LCA model suggested.
Why not 3 classes?
And 1 factor or 2
Yeah,
factors.
so here what you would do, we have explored many more factor mixture analyses than shown here. A first model that I would explore would be 2 classes, 1 factor. That is clearly rejected in favor of 2 classes, 2 factors, because you need the 2 factors. And when you have 2 factors, you're not going to need 3 classes. You don't need as many classes as in the LCA. You typically, when you have factors in the model, even if you had only 1 factor, you typically don't need as many classes as you did in the LCA where there are no factors. When there are no factors. But of course, you could go forward. What would make sense here is to actually test 3 classes, 2 factors, and we did that, and that would get a worse BIC. That is, you're introducing more parameters than you need to have. So you would see that in the BIC. Okay, we have 7 minutes left, folks. You have the energy, I hope. More.
Oh, we have a question right here in the microphone's there.
Okay.
On 174.
174.
I can do it.
I wonder, you write that no classification of individuals is obtained, but I wonder, you need this, I think.
Do you need a classification?
Yes. Otherwise, you have no diagnosis of the individuals, what they are.
Right. So this argument here that the exploratory factor analysis model gives no classification is directed towards the psychiatric tradition where they like to diagnose or classify people. And this approach of analysis doesn't give you that end result. Now, one can argue you don't need to classify people. Instead of saying how many percent are suffering from a problem and how many percent are not, why not give a score and see where a person falls in that continuum? And for instance, you could stop with the continuous factor analysis. So this is not a general critique, but a critique that's relevant for dealing with diagnostic criteria in psychiatry. Is that your question? No.
I'm a little bit confused because I think the combination is interesting to have factors and classes, but if you cannot decide on individual, then the class is only an analytical tool and it's not used in reporting results or.
But here the EFA model here doesn't have any classes. We haven't gone to the classes yet.
Oh, sorry.
Yeah, so this is standard factor analysis. Yes, it could be past the. Slide 175, a popular slide. Next.
Why you picked the last model? Because you said a chi-square difference with the degrees of freedom of 16 is significant. But I don't really get it because the BI big is smaller. I don't really get the logic, and you don't really have a chi-square there. How do you get this chi-square difference, and how did you
This is a good story, so let's tell it one more time here. So this is the factor mixture analysis where the factor loadings are held invariant across classes. It actually gives the best big of all of them. That's what you're talking about. But this model can be tested against the more general class-varying factor loading model. These two models are properly nested and fulfill the assumptions behind chi-square testing. And when that is the case, I think my own feeling is, others may disagree, is that you really should make use of that likelihood ratio chi-square test. So the likelihood ratio chi-square test gives you chi-square of 58 with 16 degrees of freedom, 16 being 75 minus 59. And the p-value is very low, saying that when you impose the restrictions of invariant factor loadings and having only 59 parameters, you significantly worsen the fit relative to the more general H1 model. So this is like an H0 model, more restricted than the H1 model. And the H0 model is therefore rejected and you go with this one. Yes, so then my feeling is when you have a choice between working with BIC and working with a chi-square difference test, I would tend to favor the chi-square difference test. Now other methodologies might argue differently, but that was the argument here, at least, to do it that way. But that's a good point. So there are certain models. I think none of the other models can be compared with respect to a likelihood ratio chi-square test. None of the other models fulfill the assumptions of being nested and not having parameters on the border of the admissible space. But these two models do. So then you might use the power of that likelihood ratio test. Yeah, that's a good point. So the question is, if you have class-varying factor loadings, you're not measuring the same dimension in the two classes. It's two different dimensions. So you cannot talk about the same dimension going through the whole distribution for both classes. And that's, that is the problem of non-invariance. So therefore, you're not going down the measurement invariance path in that tree diagram. You're almost totally exclusively going down the cluster analysis thinking that is classifying individuals in the best possible, most flexible way. But the problem is then that you cannot no longer talk about a single or two single dimensions going through all of the classes because the dimensions are different.
So and you can't therefore compare the dimensions across classes because they're not the same.
Exactly.
But rather within classes you could have different kinds of...
So for instance, that doesn't stop you. When McLachlan and the others in the microarray book from Wiley do this, they allow for total non-invariance of factor loadings, and they're not interested in placing people on the same dimension. They're only interested in clustering people. Now, if you read that hybrid article that I wrote, it also refers to IRT modeling as traditions, where people like Bob Mislevy, who used to work at ETS, Educational Testing Service in the USA, he talked about different classes corresponding to individuals using different solution strategies, and there you had non-invariance of loadings as well, of item characteristic curves. But he didn't necessarily compare people on that dimension. So you may want to read that hybrid article and look at his references. But I do agree that it complicates the modeling. By the way, there's another paper in the pipeline. I think I referred to this. A student of mine, Shauna Clark, Clarke. Do we have it in the reference list? It should be in the reference list.
Look at the paper, maybe. Copy.
Oh, yes. Slide 203. Slide 203. If you're interested in these kinds of things, here is, in her coming dissertation, this is almost finished paper, Models and Strategies for Factor Mixture Analysis. 3 examples. That goes through a lot of different modeling variations and how to use Mplus and how to think about models with and without measurement invariance. On slide 203. Shauna Clark. And she also wrote another paper that she submitted to the SEM journal relating latent class analysis to variables not included in the analysis. And that's where it comes up that using the known class, as Linda referred to, is only reasonable for further analysis, is only reasonable if the entropy is high, like 0.8 or higher. So this paper sits on our website. But the second paper is, well, it's supposed to be finished when I come back, she said. So we'll see. Okay. One more question back there.
Yeah. Actually, on the same slide or the next slide, about the interpretation, you said maybe, but I missed. Could you explain what happened to the people with the only hyperactivity? How did when we included the factors, they disappeared from the picture, but how would you interpret it?
What slide?
In plain words?
Can anybody find the nice pictures for the hyperactivity?
176?
It'll be close.
There?
Yeah.
So we said that taking a factor mixture approach, clean up the 3-class solution by dropping the potential class of hyperactivity only, almost no inattentiveness. Instead, then, allowing for factor variation around these means in each of the 2 classes. So, for instance, if you imagine I would think one can look at this by looking at the classification of people into classes, but I would think that these individuals who are here who are low on inattentiveness and high on hyperactivity are probably part of the high class over here, high class with a relatively low inattentiveness value, inattentiveness factor value. I think those people here, they're high up here, so they fit nicely in this for these items. But for these items where it's lower, it's probably captured by lower factor value for those individuals. And from this analysis, you get the estimated, not only the estimated class probabilities for each individual in each class, but also the estimated factor scores within each class. So you can really go in and take a look at how people shift between classes, say in this case, in your real analysis.
Do you have any interpretation for the two factors? I mean, medical interpretation, what type of variables are that?
So the question is, do we have an interpretation for what the factors are here?
Yes, the classes is clear, but the factors, what would that be? I mean, it's severity or something, but why two and what does this capture?
Yeah, the factors, if we don't have the estimated factor loading matrix, but it's essentially you have 9 variables of the inattention, 9 variables of the hyperactivity. So you have a simple structure where the 9 inattentiveness items load on that first factor and the 9 hyperactivity on the second, and there are no cross-loadings. So it is severity of the two different kinds. Comes out very, very nicely. Folks, it's 5 minutes past 5, and you have survived the day very well. Thank you.
Thank you.